Hi everyone, today we'll be going through the summary notes for chapter 14, periodic table. Now, periodic table is a chapter that covers a few key areas, and this is split within these notes into part A, B, C, and D. Right, so first we'll be looking at part A, where we examine the general properties of the periodic table, and then we'll go on to specific groups, starting from group 18, then group 1, followed by group 17. Right, so let's get started for the general properties of the periodic table. Now, all of us should be quite aware, and we have been using this periodic table for a while already, and we know that elements are arranged in the periodic table in a certain manner, right? And this manner is in terms of increasing proton number. So if you have to look at your notes itself, you'll know that the periodic table shows the elements, the proton number is at the top, and the mass number is at the bottom. And you realize that the proton number runs in sequence. So 3, then 4, then towards 5, 6, so on and so forth, all the way. And that is how the periodic table should be presented as, right? So it runs from left to right in what we call increasing proton number. And we also know that in the periodic table, there is this particular split between metals and non-metals, right? So, and this split occurs over here. Right? So there's this zigzag or this staircase that teachers will talk about, whereby those that are considered metals will be the one on the left-hand side of this staircase, and those that are considered non-metals will be on the right-hand side of this staircase. Now, what about some of those that are actually sitting on the staircase itself? So, for instance, elements like silicon, elements like germanium, etc., and all these elements that you see within here, so on and so forth. Now, all these elements here are what we call metalloids. Now, metalloids here, they are a bit more special in the sense that they are having properties that are similar to metals and also properties that are rather similar to non-metals. So for instance, they can conduct electricity, but then they may be brittle, right? Or they may be very strong, high density, but not able to conduct electricity. So it could be a mix of the properties. That's why we call them the metalloids. So they sit within this staircase. Now, what else do we know from the periodic table? We also know that in the periodic table, there are things called groups, right? So what are groups? Groups will be all your vertical columns. So this is called group 1, then you have your group 2, then you have your group 13, 14, so on and so forth. And there's something that we call the horizontal rows. These are our periods, right? So this is period 1, this is period 2, this is period 3, this is period 4. Okay, so how exactly are the elements arranged? This is what we need to take note of as well. In the group, which is the vertical column, the group number actually reflects the number of what we call valence electrons. Now, valence, in case you have forgotten, it means the outermost electrons, right? And therefore, what we mean is that if the element is in group 1, you will have one valence electron. And as we move from top to bottom down the group, we know that the atoms actually become bigger in size. So let's take, for example, group 1. Okay, so in group 1, we do know that for the first element, which is lithium, its electron configuration is 2-1. This means that it has 2 shells, right? 2 electron shells. Then when you go into sodium, we know that now it's 2-8-1, which means that it has 3 electron shells. So in terms of drawing wise, you know that it gets bigger and bigger. Potassium, 2-8-8-1, 4 electron shells. So naturally, the size of the atom should get bigger. Okay, so I think this is what we need to take note of for groups. But there's also one additional point that I would like you to take note of, that the group number also gives us some form of signs, right? Group number also indicates the possible, I wrote as possible because it may not always be the case, ion charge. That means if the element can form an ion, then it can very well have a charge, right? So for example, again, let's say in group 1, all the elements here, because they all have one valence electron, when they will form an ion, they will form ions of 1 plus charge, right? Because they will all lose their one valence electron, all of them will become 1 plus. So likewise, as you run through your that chapter on atomic structure or chemical bonding, that's where you can revise about how you can use group number to help you determine the charge of the ions. Alright, let's move on to the next part, which is on period. Right, so period is the horizontal rows, right, from left to right that you see. So what does a period number represent? That means when you say period 1, period 2, period 3, what does it mean? Period number actually represents the number of electron shells. So this around is how many circles that you draw out. right? So if you're in period 1, you have 1 electron shell. If you're in period 3, you have 3 electron shells, right? And we know that in the period, as you move from left to right, you move from metals to non-metals, and the reason is because the element starts to gain electrons more easily. So what do I mean by that? For example, we know that sodium can become Na plus because they lose electron. As you move from left to right, after sodium, you will see magnesium. Magnesium can become Mg2 plus because it loses electron. Aluminium, this next one, can become Al3 plus because it loses electron. Then when you reach carbon, you realize that nothing actually happens because carbon, it has 4 valence electron, it refuses to lose or gain electron. When you go to nitrogen, you realize that there is this possibility that it can also gain electron and it becomes N3 minus. Of course, we also know that nitrogen can also share, right? Because it's not just about gaining electrons only. Then you move on again, you have oxygen. You realize that it can also gain electron. It forms O2 minus, etc., etc. But we also know that oxygen can also share. Right? So it's not a case whereby, 100% you must always gain electron, because we know that for non-metals, they can form covalent bonding as well, right? So, but what we are trying to see here is that you can actually move from metallic to more non-metallic. And why? It's because you start to gain electrons more easily. That's actually the reason why we define them as metals or non-metals. Okay, so with that, we'll move on to zoom into specific groups. And we'll start with the easiest one first, which is group 18. Group 18 looks at these elements over here, right? Now, all these elements here, helium, neon, etc., etc., right? What's special about all of them is that they are what we call stable noble gases, right? So noble gases, if you look at them in terms of these properties here, so for each of these group, we'll look at 3 things, right? Number 1 is what is their physical property. Number 2 is what's the trend? Is there a pattern in terms of all these numbers that you see over here? Number 3 is how do they react? Okay, so first and foremost, you look at all of these things here, you realize that their melting point and boiling point are super low, right? It's all negative. What this tells us is that at room temperature, they'll all be gases. Why? Because they will have already boiled. Because their boiling points are all negative. That means when you reach room temperature of 25 degrees Celsius, all of these will have already turned into gas already. Last, they are all insoluble in water. But what patterns do we see? I think reading pattern is important. If you look at all these trends here, what do you see as you go down the group? Down meaning to say that you move from helium to neon to argon to krypton, so on and so forth, as you go down the group. You realize that this melting point gets less and less negative. This boiling point gets less and less negative. So what this tells us is that the boiling point and melting point actually increase down the group. So this is about reading trend, reading data, right? What else do we know is that the density also increases down the group. So they get denser and denser as you go down the group. Alright, so that is the two-part straightforward physical properties. Now in terms of chemical properties, it's good to know that for the noble gases, we all know that they have this thing called stable electronic configuration. What do I mean by that? That means they have what we call a fully filled valence electron shell. And they do not need to lose, do not need to gain, do not need to share electrons. As a result, we say that they are all unreactive, or what we call inert chemicals. I hope you remember how to derive your electronic structure, and more importantly, how to even draw them out, right? So you know that your argon will look something like this with your electrons. So all of them have what we call a completely filled valence electron shell, and then that actually stabilizes the whole element that makes them don't want to go through any reaction. Okay, so that's for our group 18, or also known as group 0. Right, so this covers the first page of this huge A3 notes, just giving you a general properties summary. But more importantly, zooming into the group period, don't take it for granted. Spend some time to understand what each of these things means. Group 18 is a straightforward group, so I'm not too worried about you understanding this piece of information over here. But as you go to the next page, when you zoom into group 1 and group 17, it can get a bit trickier, right? And there will be some video links that will be provided where I do hope that you can go in, access it, and go and explore a bit more about what the various reactions could look like, right? So the video links will be provided at the description box of the YouTube video. So do click on them to proceed to the other YouTube videos to take a look at it. Right, so let's take a look at group 1 alkaline metals. Group 1 are what we call alkaline metals, right? Hint is that they do form alkalines when they react. Okay, after they react, they will form alkalines. Okay, so if you look at all their melting point and boiling point, you realize that their melting point and boiling point generally are quite low, right? Even though I would say that when you look at this boiling point, we may think that it's super high, but for a metallic element, for a piece of metal, right, the boiling point being at 671 is really not that high, right? And of course, the melting point being low is quite obvious. What other thing is obvious is that look at the density. Metals are generally very dense, right? But look at all these elements. The density is so low, right? This is also something that is a bit unique to group 1 elements only. So properties wise, they are soft, can be cut by a knife, they have low density, and they have low melting point and boiling point. By the end of the day, they are still metallic elements, so they will still be good conductors of electricity and heat. Right? All of them can flow on water because they have most of them, these three can flow on water because they have low density. Right? Water has a density of 1 grams per cm cube. So as long as they are lower, they can float on top of water. Okay, so what's the trend that we see over here? We do see that there's a trend in terms of the melting point and boiling point as you go down the group, the number actually decreases. Yeah, and we also notice that the density actually increases as you go down the group. Right, so these will be the two trends for the physical property that you see over here. Okay, so as I'm going through the next segment on part 3 as well as part 4 later on, do take note that it'll be helpful for you to click on the video links in the description, right, so that you can go and explore how these reactions look like visually, and it will help you to remember how the trend should be like. Okay, so first and foremost, group 1 metals are super reactive and they should always be handled with care. What do I mean by that? Even if you just expose them to the air, leaving them on the table, they will go through reaction as well because there will be oxygen. And this is what we call as tarnishing. Right? So it's a form of corrosion that happens. As a result, what we do is that we always keep them inside what we call mineral oil. Right? Mineral oil is prevent contact, right? Prevent reaction with oxygen or even the moisture around the atmosphere. Right? So you look at this over here, these group 1 metals here, they are actually stored. Don't think you can see the level. There's a level over here, right? These are all mineral oil inside. Then they are kept inside so that to prevent them from interacting with oxygen or even water vapor in the atmosphere, right? So if not, they will go through certain reactions, and that's how reactive they are, right? And why are they so reactive? It's because they only need to lose one valence electron to react, and that will mean that they will be super reactive because like just one electron gone and there's a reaction that will happen already, right? So that is why when you look at group 1 metals, right, we realize that there's a trend that's very interesting that when they react, if you look at lithium, sodium, potassium, the reaction gets more and more violent, right? It gets more and more you will see flame, right? And these are the unique traits of a group 1 metal reacting with water. Okay, so this is a reaction with water itself, right? And when they react with water, they will always form metal hydroxide and hydrogen gas. This is similar to what I learned in the chapter on metals, right? Because all metals, when react with water, will form metal hydroxide and hydrogen gas, right? But for group 1, what's unique is that you realize that they do float, especially if their density is lower than water, because they generally have low density. Right, if you go even further down, you realize that things like rubidium and cesium, they're so reactive that it may be violent, it may explode, it may catch fire, right? So you see a trend over here, and the trend is that the reactivity actually increases down the group. Okay, so what are we saying over here? We're saying that group 1 metals are so reactive that whenever you place them with water, they can form metal hydroxide and hydrogen gas. And what is more important is that the trend actually shows that there's an increase in reactivity. Okay, and for the second column over here, it reflects the equation that we're looking at. So in this case, we know that to balance it, we need to know that lithium is a Li plus, hydroxide is a OH minus. Therefore, when they form a chemical here, it'll be IOH. Likewise, if sodium is a Na plus, OH minus, it'll be NaOH. K plus, OH minus is a KOH. So of course, balancing of equation is a skill by itself, and that's something that we'll be practicing throughout the entire 2 years of the upper sec education, right? So that's quite standard, and give yourself time to practice until you get the hang of it. And of course, do take note that testing for hydrogen gas is part of the syllabus that we have learned before, right? So you can use the lighter spleen, and you should know what should be the observation that will happen if there's hydrogen gas. So that is for our group 1 alkaline metals, right? So alkaline because when you put them into water, they form your metal hydroxide here, and these are all alkalines, your LiOH, NaOH, KOH. Okay, so that is something that we spoke about. Low density, soft, elements, low melting point and boiling point, can react very easily. That's why you store them inside oil. But then if you react them with water, these are the reactions that you'll see because they get more and more reactive as you go down the group. So that's for group 1. Let's take a look now at group 17, which are our halogens. Now group 17, if you look at the right side of the chart, focusing on this part, you'll notice that they have a certain set of melting point and or rather a certain set of boiling point as well. And you can see that they are generally negative or even in the lower numbers. That's why their physical property is generally that they have low melting point and boiling point. But what is also interesting about group 17 elements is that they are they are all colored. Colored meaning to say that not because I use color to show the molecules over here, but the chemical itself has a certain color, right? And what is that certain color of the chemical? Is that for fluorine, it has a pale yellow color. For chlorine, is yellowish green. For bromine, is reddish brown. And for iodine, it could be a black solid or it could be a dark purple solid, right? And you look at the physical state, you realize that at room temperature, it goes from gas to liquid to solid because there's an increase in the boiling point. The number gets bigger as you go down, right? What else do you notice about the color? How does the color intensity change? How does the darkness of the color change as you go down? It should get darker and darker. Alright, so this too shows the trend in terms of the physical properties, right? So melting point and boiling point increases and color intensity increases down the group. Right, so remember, just take note that you first learn about physical properties, then you talk about the trend in physical properties. Now, in terms of chemical properties, what's interesting about group 17 is that they are also quite reactive, but there is something that they react in, and that's what we call a displacement reaction. Now, displacement reaction is something that we will see in the chapter on metals, right? But to just give an easy snapshot of what it looks like, just imagine an analogy of a couple. So, a couple in a relationship over here, and suddenly there comes a third party. Okay, maybe this third party is more attractive, more good-looking male, for example, in this case, for this example, right? So what will happen is that, assuming that this is more attractive as compared to this other male here, which is less attractive, in this very simple way of giving an analogy, what will happen is that this couple will actually split or break up because this more attractive male, for example, will then take over the role, and then this less attractive male, for example, will be left forever alone outside. This is a good example of what displacement looks like. It's essentially a case whereby you have a couple and then you have an individual that comes along, but this individual can be compared to one of the partner within this relationship, and there's a difference in terms of the attractiveness, and then there can be a swap, right? And what this shows is that what must be present is one must take the place of another in a compound or in a relationship. And how do we recognize that? A more reactive halogen will displace a less reactive halogen from its halide compound in a solution. So halide refers to the compound of a halogen, right? Displace means to take the place of something else. So putting all these things together, you will realize that it's possible for one halogen or one group 17 element to pick away the other group 17 element and then form a new chemical, right? So what it could look like is, for instance, imagine inside this container here, you have a compound that contains a less reactive halogen. So give you an example. Let's say we say that this is maybe you say it's Ki, potassium iodide, and then this more reactive halogen. Let's give an example. Say is chlorine, right? If chlorine is more reactive than the iodine, because this is a couple, right? This is in a compound Ki. Chlorine will displace the iodine, and then you form a new compound. Displacement will take place. But on the other hand, if you have a compound that contains a more reactive halogen, which for instance is like Kf, and then you were to put in a less reactive halogen, let's say it's iodine, because iodine is less reactive than the fluorine, it will not be able to displace the fluorine from the reaction sheet. So it's very much like how you look at it over here, whereby you have a couple, which is a compound. You have an individual element, which is the one that challenges to see whether it can displace or not. Then you see whether it happens or not. Right? So how does this whole thing work out to be? Basically, we need to first know that there is a decrease in reactivity of halogen down the group. What this means is that fluorine is the king. It's the most reactive one, followed by bromine, followed by chlorine, followed by bromine, followed by iodine, followed by acetylene. Right? So there is this trend. When there's this trend, what it tells us is that if today we were to put chlorine with potassium chloride, we are trying to look at whether chlorine can challenge this chlorine inside this potassium chloride. And of course, if you think about it, it doesn't make sense because both are the same elements, right? Chlorine versus chlorine. There's no need to even discuss about whether it can replace the chlorine or not because they are the same element. Likewise, if you look at the second row, bromine versus potassium bromide, no point because bromine and bromine, they are essentially the same element. And for the last one, iodine and iodide, no point because they are essentially the same element. Right? So there's no need to compare for these three that put a dash over there, right? Naturally. But if you look at the subsequent ones, you can start to think about it. Chlorine now put together with a chemical called potassium bromide. You're trying to compare chlorine to the bromine and asking yourself that do you see that there's a difference in terms of their reactivity? And if there is, which in this case, chlorine is better than bromine, what this tells us is that a reaction takes place. And what happens in this reaction is the chlorine, when you react with the potassium bromide, will actually displace the bromine and form potassium chloride, and the bromine comes out. So that actually takes place. If you have to take a look at, you may want to pause the video first to copy down this part before I go on to the next box when I'm explaining so that you can focus, right? If you look at bromine versus potassium chloride, so you're comparing bromine and chlorine. And if you look at this part, is bromine more or less reactive than chlorine? Must you know that this is the lonely challenger that's coming to the couple of the compound. And you realize that bromine is less reactive than chlorine. And what it means over here is that there is no reaction because bromine is less reactive than chlorine. Sorry that I overspilled from the box, but try to write within the box itself. Right, so this is actually what happens over here. Okay, how about the next one? Iodine compared to the chlorine inside potassium chloride. And you realize that likewise over here, iodine is less reactive than chlorine. And once again, there will be no reaction, okay, as I is less reactive than Cl. And that is what displacement is about. You need to be able to look at the lonely challenger coming in and compare to that exact chemical inside the compound to see whether there can be a fight, a challenge. Right, so likewise, if you take iodine compared to potassium bromide, looking at the reaction between this iodine and this bromine, you realize that once again, not possible because iodine is less reactive than bromine. So what it means is that no reaction as I is less reactive than Br, so cannot do any displacement. Right, same logic, apply this and do it for yourself. Bromine compared to the iodine, do you see a comparison? If there is, take note, write for yourself whether is it more reactive or less reactive. Chlorine compared to potassium iodide, over here this element, look at it, compare for yourself, see whether it's more reactive or less reactive, right? Then of course, pause the video now, try to complete these two boxes yourself, right? In about 5 more seconds, we're going to run through what it could look like. Right, so I hope you have given yourself the chance to try to attempt these two boxes instead of just filling up the blanks. Right, for this one, we know that chlorine is more reactive than iodine, and this one, bromine, is more reactive than iodine. So naturally, for both cases, reaction will take place. But I hope that you can take this chance to practice writing out the equation yourself, right? And that's something that you have to own this piece, right? So you know how to construct the equation yourself. right? But this would be how group 17s are like. Now, to zoom out to what page 2 is about, page 2 actually zoom into group 1 and group 17 in more details, and you realize that group 1 and group 17 are the more interesting elements in the periodic table because now they have reactions, they can show trends, they are more interesting, there's more colors, there's visuals to the reactions, right? Okay, remember to click on the link to the videos so you can examine to see what's going on. What I mentioned, take that for group 1, they're all very reactive and reactivity increases on the group. And for group 17, they are also reactive, but reactivity decreases down the group. But what's interesting about group 17 is that there's this whole big concept about displacement that you do need to take note of, right? And displacement also features in the part on metals and reactivity series in the chapter. Okay, if not, that's all for the summary on periodic table. The next step is to then practice the questions that is presented to you in the worksheets or in the topical 10 series. Thank you.